This week, we're going to start talking about some stuff that is probably going to be among the more practically useful topics that we'll have. And from here on out, I imagine we'll have more and more practically useful topics, moving away from the theoretical stuff into the useful stuff. And so this week, we're starting by talking about inferences about two mean vectors. And so this is the sort of corollary to the most common type of t-test we would see in our regular univariate analysis. So when we make inferences about two different means from two separate samples in a univariate context, what is the procedure that we usually use? We use an independent sample t-test. And in principle, this is the same as what we've seen when we were looking at one and paired sample situations last week, but there's one new consideration. What's that? What might be different when we have separate samples as opposed to two measurements of the same sample in the paired case, for example? We might actually have two different variances, and we might even have two different sample sizes in our two groups. And to account for this, we have to pool the observed variances or the standard deviations. And remember, we're still assuming the populations have equal variance. That's one of the assumptions of our t-test. But we might, that's an assumption about the population, not the samples that we've drawn. And in all likelihood, the samples will be have at least slightly different variances. So to pool variances in the univariate case, we use this formula, this fun-looking formula. And so really all this is saying is that we're taking the sums of squared errors from both groups, which is the numerator of a variance term, and we're summing them together and dividing by the degrees of freedom. So essentially we're weighting the variances by the sample sizes. And so we each group individually has degrees of freedom n-1, so we divide by n1 plus n2 minus 2. And then we get our pooled variance, and we can convert that to a pooled standard deviation by taking the square root, and that gives us our independent sample t-test, which is the difference in the means of group 1 and group 2, divided by the pooled standard deviation times the square root of the inverse of the sample size. So this is really an extension of what we've already been seeing, which accounts for this issue of the groups having different variances and different sample sizes. So we can work just like last week to rewrite our univariate t-test into something that's more in the form that we've seen with t-squared. So first we square both sides, and then we can rearrange it into something that looks a little bit like this quadratic form almost, and that's the t-squared. And once we're there, we can essentially just substitute in our mean vectors for group 1 and group 2, and our pooled covariance matrix. And that's really the trick that we have here. We have to get the pooled covariance matrix, and that's the one sort of wrinkle that we really need to learn about this week. And this is still just a straightforward generalization of what we know. The main thing is that if you remember back in lab 3, we talked about that the multivariate generalization of sums of squares was sort of a special thing that was not quite just sums of squares. Does anyone recall what it is, what the extra piece that it had is? So it's sums of squares and cross products. And so the reason is that it also, the sums of squares only has the squared error between a variable's mean and its observation. This also has the cross products between the areas of different variables. And so we denote the sums of squares and cross products matrix with Q because SSCP is a mouthful. So instead of pooled variances, we need to get the full pooled covariance matrix. And to do this, it's essentially just exactly what we've seen, except we're getting these Q matrices in the numerator instead of sums of squares. And so that we just do the same thing, divide by n1 plus n2 minus 2. So once we have that, we can plug everything in to our t-squared. And just, if you want to look at the slide a little bit more, if I'm going too fast, just note that here what we're seeing is we're taking variable 1 minus its mean times the observation of variable 1 minus its mean transpose. So this is essentially a row of observations. So this would be the first. This would be the the set of observations across our p variables for participant number I, and we're subtracting from the mean vector, which is also of length p. So these are both p length vectors of variables where each xi is an observation. And so because these are both, this is going to be a p by 1 minus a p by 1. This is also going to be a p by 1, and this is the same thing, just transposed, so it's going to be a p by 1 times a 1 by p. That's going to give us a p by p. And so we keep adding up the p by p's for group 1, that gets us q1, and then we keep adding up the p by p's for each row for group 2, and that's going to get us group 2. So like I said, now we can plug everything into our multivariate t-squared. So we're just doing exactly what we've seen. We're taking the difference in the mean vectors. We're multiplying by the pooled covariance matrix times the inverse of the sample sizes. We're taking the inverse of that matrix. And then again by our the difference in our mean vectors, because we're squaring it essentially. And so this is our new version of t-squared, which is still distributed proportional to an f, but we'd have to do some rearranging to get it onto the f distribution. So we rearrange by multiplying it by n1 plus n2 minus p minus 1 divided by n1 plus n2 minus 2 times p. And that gets us an f statistic, which we can compare to an f distribution with p and n1 plus n2 minus p minus 1 degrees of freedom. And so here's a simple example that I found just on Kaggle, which is a website that has lots of free data sets. This one just has the weights and heights of several thousand people. They collected gender information from them. It looks like they just asked male or female, which probably isn't what they should be doing, but that's what they did here. So it's a very nice, simple example where we have two different variables that we imagine are correlated. We imagine height and weight are not uncorrelated. And we can compare the two groups. We can see if weight and height are simultaneously different for males and females. And so the first thing I'm going to do is I'm going to subset my data so that I get only the data for group 1. So here I'm just taking the two weight and height variables that I'm interested in for the cases where gender is female, and then in group 2 I'm doing the same for the cases where gender is male. So next I'm going to get my sample sizes. So I'm going to get N1 and N2. So we see that in this particular data set, which I did subsample to make it unbalanced, just so, because that's more likely how the data we're going to see is. In the full data set, there were actually the equivalent, I think there were 5,000 of each. But here we see in this data, the subsample that I randomly chose, we have 2,502 females and 2,429 males. And of course, there are two variables. So I'm just going to set P equals the number of columns in one of my groups. So that's 2. So next I'm going to get both of my Q matrices. And so we could do this the way we looked at back in lab, or we could use the formula that I showed you a few slides back. Those are both more complicated than we need to be. So one thing that you'll note, if you look back at lab 3, we noted that the way we get S, which is the covariance matrix, is we essentially divide Q by n-1, which is the degrees of freedom. So a simpler way we can do this is to use the cov function, and so to get our covariance matrix. And if we do that, we can rearrange things where just Q is equal to S times n-1, just using the algebraic manipulation from that. So it's a much simpler way to get the Q matrix here. So here you see I get my Q matrix for both groups just by multiplying the sample size of the group -1. So those are my two Q matrices. So now I can get my pooled covariance matrix by summing the two Qs and dividing by the total degrees of freedom, n1 plus n2 minus 2. And so that gives me my pooled covariance matrix, which I'm calling SP here. And of course, I need my the means for both of my groups. So here I'm just getting the means for both variables for group 1 and group 2. So we can already see there's some differences in these means, but we still need to test them. So next I'm going to get my t-squared statistic, and this is just following the same formula that we saw several slides back. I tried to make the code nice and generalizable by naming everything in this way. So here I just have x bar 1 minus x bar 2 times the inverse of the pooled covariance matrix times 1 over n1 plus 1 over n2, and then again times x bar 1 minus x bar 2. So this just matches up exactly the formula that we looked at several slides back. So this is our t-squared statistic. We convert it to an f value using the appropriate degrees of freedom, the way we looked at, or the appropriate proportional transformation. So we multiply by n1 plus n2 minus p minus 1 divided by n1 plus n2 minus 2 times p. And so that gives us our f value. And so to get the p value, we plug in our f value with p and n1 plus n2 minus p minus 1 degrees of freedom, set lower tail to false. And you see it comes out as 0 here. This is actually not quite 0. A probability from this distribution will never actually be fully 0. This is just lower. This is going to decimals so small that r can't help itself but round off. So this is really just p is tiny, 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 tiny. So that tells me that there is a difference between my two groups on height and weight. And so here we see we can use the T2 test function where we just enter both groups in, and that'll automatically give us two sample t squared. We can also use the formula syntax for the T2 test function, and this is just often easier because you don't have to subset the data first. So here I'm just combining weight and height and testing by gender, and this is the exact same output, you'll note. So that's how we do the two sample t-test for more than one variable at the same time. So the joint multivariate t-squared. So we can also get confidence ellipses. So just like last week, what we saw last week was that we get our confidence ellipse by drawing around the eigenvectors and eigenvalues. So this is the one sample case with this formula. To do the two sample case, we just have to expand it out so that we have the difference in the two mean vectors plus or minus the eigenvalue. And again, we have to use we have to weight by the appropriate sample size. So we take 1 over n1 plus 1 over n2 instead of this replaces this n here down here in the denominator. So we're taking this, and that notice that takes that guy's place, and then we have the similar proportional f transformation to get it back into t squared, and then we multiply by the eigenvectors, and these are the eigenvectors and eigenvalue from the pooled covariance matrix. So this is the same that you saw last week. So I'm just getting my eigenvalues as my lambdas, my eigenvectors as my e's. I'm getting my critical f value for my degrees of freedom. And I'm getting the distance, which is by multiplying this 1 over n1 times 1 over n2 times the proportionality of the f. So this gets it basically back into the t squared metric, which is an appropriate distance. So then I get the distances along both of my my eigenvectors and eigenvalues. And so I couldn't find a good automatic plotting function for this one, so I tried to simplify everything from the steps so you could actually see the code that I used and have it make some sense maybe. So you can essentially plug into this code to get the plot if you ever really want it. It's not something that gets done that frequently, but it's good to be able to see what it looks like. And if you wanted to adapt the code, I tried to make it a little bit easier than what I had before. So this is just an adaptation of the code that I have been using. I changed it around a little bit to make it slightly simpler. So the key really is that for the actual lines for the vectors, you just plot them as the difference plus or minus the two distances, d1 and d2. But for the ellipse, you use the stat ellipse function in ggplot, and you have to divide the distances by pi. So you can't just use the actual distances; you have to divide them by pi. And so here's the code at this point that you can use. And again, you should just be able to adapt this straight away if you ever want to do it. And again, this also only really works in the 2-variate case where p equals 2. Beyond that, we can't really visualize, but this gives us our confidence ellipse like we've seen. So this is the 95% confidence ellipse for the difference. I'm not making you do this. This is really just for your reference. And it's more important to see this conceptually, what this looks like. So this is, we would say that jointly 95% of the time, the sampling distribution of our two means should jointly be inside of this ellipse. 95, we can move with 95% confidence. So we could also get the simultaneous 95% confidence intervals. And so remember, these are just representations of the extreme values of this confidence ellipse on each variable separately. This is the same thing as when we were looking at the boxes that surrounded the ellipse last week. And so unfortunately, the MVCI's function does not seem to work for the 2-sample case, and I couldn't find a great function for it. So for now, we have to do this by programming it by hand. This is the formula that we use. So this is pretty much the same, just the generalization of what we saw last week to the 2-sample case. So for each variable, we take the difference in the means, and then we multiply by the square root of our F proportionality transformed to a T. So this is pretty straightforward. This is just our critical F value. And then we multiply by the square root of the pooled variance. So we don't need the covariance for this node. We just need the variance. That's what SII means. This isn't the full covariance matrix. So pretty straightforward to do this. So here's the code that you can use. You don't need any of the other plot stuff for this. You just need the two means. So here I take the difference in the first mean, the mean from the first mean from group 1, the first mean from group 2, and I just enter in everything from that previous formula that we saw. Really, the only things that we're going to be changing here are these indexes, because so this index means it's the first mean from group 1, so the first mean from group 2, and then the first variance. So because we have the full covariance matrix, the first diagonal element where I equals j, that's going to be the first variance. So this gives me the upper and lower confidence interval for the simultaneous confidence interval for the first variable, and then for the second variable. All I have to do is change this part in the square brackets. So we get the difference in the second means and the second diagonal element of the covariance matrix, and that gives us our simultaneous confidence interval again. And to get the separate confidence intervals, we can always pull this out of the t-test function. There's probably some CI function that would do this as well, but in this case, since we're doing 2 samples, we can always just pull it out. I mean, you could do this the same way with a 1-sample case as well. So to pull it out, you just one of the things that the t-test function outputs is a confidence interval, and so you can just if you didn't add this $ confident part, it would give it to you in a larger output. But if you just want the confidence interval, you could include $ confident, and that'll give you confidence interval. And of course, if we want the von Ferroni adjustment, we just have to adjust the confidence level. So in this case, we're going to change it to 1 minus alpha divided by p. So 1 minus 0.05 divided by p. And that gives us our von Ferroni adjustment. It gives you the actual confidence level here as well. But we sort of ignore this because we're treating this as a 95% confidence interval because we're making the von Ferroni adjustment.